Hi, welcome back to the lecture series on abstract major theory. In the previous lecture, we have seen some algebraic properties of collection of measure. But we have also seen that the scalar, the negative scalar multiple of a measure is not a measure, and that's why in this lecture we are going to discuss signer measure. Because in case of silent measure, we can define scalar multiplication with respect to any real number. So let's first define signer measure. Okay, let's discuss signer measure. Okay, so a set function mu, a set function mu from this sigma algebra to R star. So R star means extended real number system, means that R star is actually R union this set minus infinity and plus infinity. So it contains both infinity as well as plus infinity as well as minus infinity. So the values of this set function lie in this R star, which contains which is a set of real numbers together with two infinities, minus infinity and plus infinity. So it's a positive as well as negative valued function here. Is said to be a signer measure. Is said to be a signer. Is said to be a signer measure. Is said to be a signer measure if it satisfies the following properties. If it satisfies the following properties. First property, it should assume at most one infinity. So mu assumes at most one infinity. Mu assumes at most one infinity. At most one infinity, one of the values plus infinity and minus infinity. It should not assume both the infinities, okay, because this will create problem. So that we'll discuss later on why it should assume only one infinity, either plus infinity or minus infinity, or it should it should not assume any of the value. If it assumes infinity values, it should assume at most one, either plus infinity or minus, not both the values. And property second is that the mu of the empty set should be equal to 0. And third property is that it should be sigma additive. Mu is sigma additive. Mu is sigma additive. Sigma additive means that is given a disjoint sequence, a n in sigma we should have this mu of the disjoint union a n runs from 1 to infinity is equal to summation n runs from 1 to infinity mu of a n. So these are the three properties of signer measure. First property, it should assume at most one infinity, plus infinity or minus infinity. Second property, mu of the empty set must be equal to 0. And third property, mu is sigma additive. Okay, so these are three basic properties. So why it should assume these only one infinity, not both? So this mu is suppose if it assumes two values. See, if it assumes two values, see, plus infinity as well as the minus infinity, with the condition that these sets are disjoint. Suppose there are two sets A and B in sigma such that A intersection B is the empty set, they are disjoint, and mu of A is plus infinity, mu of B is minus infinity. Okay, suppose it assumes both the values, plus infinity as well as minus infinity. Then what will be mu of A union B? It's equal to mu of A because it's sigma additive, so that means it should be finite additive also. This is plus infinity minus infinity. It's infinity minus infinity, so it's indeterminate, and we cannot give the proper meaning to this value because it vary actually. It's indeterminate form actually. So either it's not another infinity, neither plus infinity nor minus infinity, or it's not a unique. It's not actually a unique value. So it is indeterminate. So this will create the problem because we don't have a proper value for this union actually. So that's why this mu should assume at most one infinity, either plus. If it assumes plus infinity, then there does not exist any member in this sigma such that the value of the mu at that member is equal to minus infinity. So if it assumes one infinity, suppose plus infinity, then it should not assume this minus infinity. Okay, if it assumes minus infinity, then it should not assume plus infinity. Okay, so that's it should assume at most one infinity, or it should assume neither of these infinities, neither plus infinity nor minus infinity. If it assumes infinity values, it should assume only exactly one, either plus infinity or minus infinity. And one more thing you can see from the definition, because given a disjoint sequence is an, it's equal to say a1 a2, it's like this, it's a disjoint sequence. So if this set is same as this, a I1 a I2, so on a in, and so on up to infinity, while this I is the permutation of this. So I1 may be equal to 2, I2 may be equal to 5, I3 may be equal to 1. So I'm choosing the different, I'm permuting these sets. Okay, so it's the same collection. Then you can see this union an is same as union a this in. Okay, and runs from 1 to infinity. Both the unions are same. So that means their mu values must be same. So this union an runs from 1 to infinity is same as union a in runs from 1 to infinity. Both the unions are same. So that since mu is a set function, it's a function, this means that their mu values must be equal to same. So this step is very important. Okay, both are disjoint. So on this side it is a summation mu of an, and on this side it's a series mu of a and I. So this the sum on the right hand side, it's actually the rearrangement of this series. We are permuting these numbers actually mu a, but the value must be same. So that means rearrangement of these terms does not alter the sum. As you have seen that if the series is conditionally convergent, as you have seen in this courses in analysis, if given a series an which is conditionally convergent, then for any real number a, whether infinity, plus infinity, or minus or finite, any number, any real number, or any of the infinity, plus infinity, or minus infinity, I can rearrange this series so that the sum will be equal to that a. That's the rearrangement series. If the given series is conditionally convergent, then I can always rearrange this series in such a way so that this series will converge to any particular, to any number which I have already chosen. So given any number, I can rearrange this series to make the sum equal to that number. But here is the problem, that if you choose any rearrangement, this sum will never change. So that means the series is actually absolutely convergent. It's not conditionally convergent, it's absolutely convergent. So we can say that this series mu of an, where an is a disjoint, so you can say in sigma, this is absolutely convergent. This is absolutely convergent. This series is absolutely convergent. So which means that the series n runs from 1 to infinity, mod of mu of an is convergent. Is convergent. Okay. So that's very important to find here. This is not conditionally convergent, because for any rearrangement the series is the same. The sum of the series remains the same. It will not converge to any arbitrary point. So now next we have an exercise. Show that every measure is a signed measure. Show that every measure is a signed measure. That's very simple. That's not too difficult. And next exercise. Show that signed measure is finite additive. Show that signed measure is finite. And finite additive means that is mu of the finite union ak. K runs from 1 to n. This is true for a measure. Now you have to prove this also holds for signed measure. The proof is similar, okay? But these AIs, they are disjoint members, okay? This is the NPT set for I not equal to J, and these AIs, they belong to sigma, okay? So they should be in the domain. So this is the second exercise. Every signed measure is finite additive. It is sigma additive. That's from definition. Now next we prove the following theorem, which is also true for measure. Now we prove the analog of that theorem in signed measure, which is measure of difference is equal to difference of measures. Let mu be a signed measure. Let mu be a signed measure. Let mu be a signed measure. Let mu be a signed measure on sigma, and let A belongs to sigma be such that its measure is finite. Mod of mu of A is finite. If B is any member of sigma such that B is subset of A, then the conclusion is, then you have to show the mu of A minus B is equal to mu of A minus mu of B. So mu of difference is equal to difference of mu's. So mu of measure of difference is equal to difference of measures, you can see. Proof इसका बहुत simple है. It follows on similar lines as in case of measure. You can see. So let's prove this theorem. So obviously we have following identity, because we have this A is the bigger set and B is the smaller set. Where the situation like this is B, and this is the set A, okay? So actually this A is equal to this portion and then this portion. What is this portion? This shaded portion? It's a minus b. So you can see this clearly. This a, which is equal to a minus b, that shaded region, a minus b union b, and these are not disjoint sets, and both are the members of sigma, because sigma is a sigma algebra, okay, and sigma algebra is closed with respect to difference. So it gives that, this implies that mu of a is equal to mu of a minus b plus mu of b. Okay, this mu of a, it's a finite number, so that, and mu assumes at most 1 infinity. So suppose if it assumes plus infinity value, okay, then both the mu values must be finite numbers, because suppose if one of them is plus infinity, say it's plus infinity, then this is some finite number plus infinity, it's equal to plus infinity, which is not the case because mu of a is finite. And suppose this one is plus infinity, then this is plus infinity plus some finite number, so this is again infinity, which is not the case. So and similar line, if it assumes a minus infinity value, suppose for this b, mu of b is minus infinity, then this is a finite number, because this cannot be plus infinity, so it cannot be infinity minus infinity. That situation cannot arise here, because from the definition of finite measure you can say. So if it's minus infinity, then this must be a finite number, or it may be minus infinity also. So it's minus infinity, that's again minus infinity, or if it is finite number minus infinity, which is again minus infinity. Same is the case for plus infinity. Suppose mu of b is plus infinity, then this may be a finite number or plus infinity, not minus infinity. Okay, so it's a infinity plus infinity or finite number plus infinity. So that's again infinity, so which is not the case. So since mod of mu of a is finite, this implies that mu of a minus b and mu of b are real numbers. They are real numbers, means they are finite, okay, or real numbers. So therefore we can transfer this side. Mu of a minus b is equal to mu of a minus mu of b. So both are numbers, so that means mu of b is also finite. It's finite number, so they are real numbers. So from this lemma we can conclude that this is the remark. You can see this is the remark. If a set A belongs to the sigma algebra, has a measurable subset, has a measurable subset of infinite signed measure of either plus infinity or minus infinity of infinite signed measure, then A itself has infinite signed measure, then A same infinity, okay, itself has infinite signed measure, so this A, it's a member of sigma. If this A has some subset, has infinite signed measure, then A is also infinite signed measure. How if possible this A has finite signed measure, then every subset of A has also finite signed measure by previous theorem. So therefore whenever this A has a subset of infinite signed measure, then A must has infinite signed measure, because if it has finite signed measure, then every subset of A has finite, but here it is given that it has some subset having infinite signed measure. So this A must have infinite signed measure. Okay. So next we have a theorem that follows on similar lines as in case of measure. So I will not prove this theorem here. You can see the proof from Alprints. Okay. So for a signed major mu, 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 and a sequence an of sigma and a sequence an of sigma, the following statements hold. The following statements hold. First statement, if an increases to a, so that you know what do we mean by an increased to a. An increases to a means that this an is a decreasing sequence and the union of these an is equal to a. Okay, that means an, that's the meaning of this an increases to a. तो ये आपने ऑलरेडी किया है इसका फर्स्ट कोर्स ऑफ मेजर थ्योरी, वहाँ पर हमने इसको डिस्कस किया है. एन इंक्रीज टू ए का मतलब ये है कि ये जो सीक्वेंस है ये इंक्रीजिंग सीक्वेंस है सेट्स की. इंक्रीजिंग का मतलब क्या है, ए1 सबस्टफ ए2 सबस्टफ, दैट्स इंक्रीजिंग, और इनका जो यूनियन है वो ए के बराबर. तो ये नोटेशन है एक्चुअली, और नोटेशन का मतलब मैंने बता दिया, इट इज इंक्रीजिंग एंड यूनियन इज इक्वल टू ए. ओके, सो इफ एन इंक्रीजेस टू ए then mu of an, now they are not sets here, they are now real number. Mu of an increases to mu of a, तो रियल नंबर्स में इंक्रीजिंग का मतलब क्या है, इसका तो एक सीक्वेंस है रियल नंबर्स की, इसका मतलब ये है कि ये इंक्रीजिंग सीक्वेंस है और इस सीक्वेंस का लिमिट ये है. सो दैट्स दिस mu of an increases to mu of a. And the second part is if an decreases to a, so decrease का मतलब क्या है, this sequence is decreasing means a1 contains a2, a2 contains a3, a3 contains a4 and so on and so forth, और इसका जो intersection है वो a के बराबर है. And one more condition is that mu of ak is finite. Finite means it's real number. Okay, mu of ak is a real number, is a real number for some k, for some k. Then mu of an decreases to, then mu of an it decreases to, oh, it's not decreasing, so sorry, so here the conclusion is not increasing actually. This limit, okay, its limit is this, and its limit is also mu of a. It's not increasing or decreasing because we have not seen that whether this signed major is monotone or not. So we cannot say this, if n is increasing sequence then the corresponding sequence is also increasing. This cannot be said here. So this limit of mu of an is equal to mu of a, and in this case also limit of mu of an is equal to mu of a. The proof is similar. For the proof, see theorem number, what's that theorem number 15.4 on elephants. इसको मैंने ऑलरेडी एक्सप्लेन किया है फर्स्ट कोर्स ऑफ मेजर थ्योरी जो आपने किया है, जो ऑलरेडी अपलोडेड है यूट्यूब चैनल पर, वहाँ पर आप इसको देख सकते हो. दिस थ्योरम 15.4 on elephants. Okay, next, since we are in signed major, therefore we can define positive set, negative set. In case of major, we don't need to define every set is their positive set. I will define positive and negative set here first. Then you can see in case of major, every set is actually a positive set. But in case of signed major, we can define two types of sets. One is the positive set and second is the negative set. Now this is the definition of positive set. A measurable means it's a member of sigma. Okay. A measurable set A is said to be a positive set, is said to be a positive set, is said to be a positive set with respect to a signed major, with respect to a signed major mu, and in symbols we say this, in symbols this can be written as, in symbols we write this as positive. In symbols we write a is greater or equal to 0, means that a is a positive set, is a whenever, and when it's positive set, whenever its measure of every subset of a is positive for every member A of sigma. Or equivalently we can say that this set A is positive if its measure is positive and every subset of A has measure positive, then we can say it's a positive set. Equivalently can say equivalently as set A belongs to sigma, as set A belongs to sigma is a positive set, is a positive set if mu of E is greater or equal to 0 for every subset E of A with this E belongs to sigma. So in particular mu of A must be greater or equal to 0 because A is also subset of A. And similarly we can define negative set also. So what's negative set? As set A belongs to sigma is a negative set, if mu of E intersection A is lesser equal to 0 for every E belongs to sigma. Or equivalently we can say equivalent A belongs to sigma is a negative set, if mu of E is lesser equal to 0 for every E subset of A with E belongs to sigma. And we write if A is negative set, and we write it as A is less or equal to 0. So that's the definition of negative and a positive set. Now next we have an exercise which states that a countable union of a positive set is again a positive set. Show that countable union of positive sets is again a positive set. In a positive set, countable union of positive sets is again a positive set. Solution is very simple. Let an be a sequence of positive sets. We show that their union A, which is the union an runs from 1 to infinity, is also a positive set, is greater or equal to 0. Is greater or equal to 0. Okay. Let's define the following sets. Define. I will try to express this union as a disjoint union. For this, I will define B1, which is equal to A1, and in general Bn it's equal to An minus union Ai. I runs from 1 to n minus 1. So then you can see that this Bn is subset of An, then Bn is subset of An for all n greater or equal to 1, and the union Bn is same as union an, which is A. Okay, this is simple. But this and this Bn and this Bn is a disjoint sequence, is a disjoint sequence of positive sets. Why it's positive? Because it's subset of an. An is positive, so that means Bn is also positive. Any subset of positive set is positive. तो पॉजिटिव सेट का मतलब क्या, उसके हर किसी सबसेट का मेजर पॉजिटिव होना चाहिए. अब अगर an पॉजिटिव है तो इसका जो भी सबसेट होगा उसका मेजर पॉजिटिव होगा. इसका मतलब है कि bn का जो भी सबसेट होगा उसका मेजर भी पॉजिटिव होगा, क्योंकि वो एक्चुअली an का सबसेट होगा. तो bn पॉजिटिव है. तो bn is a disjoint sequence of positive sets, and they are also measurable, in fact, because it's the difference of two measurable sets. Okay. So it's a disjoint sequence of positive sets. It's a disjoint sequence of positive sets. Now we have to show that this union Bn, okay, it's a positive set. It's a positive set. So we apply the definition here. Let the first part of the definition, not the equivalent part, that E belongs to sigma, be any member of sigma. Then we show that mu of E intersection A is positive. That's a definition. That's a requirement for the set A to be a positive set. It's equal to mu of E intersection A, but A is a disjoint union and runs from 1 to infinity Bn. Okay, and this is equal to mu of union and runs from 1 to infinity A intersection Bn. Now what are these intersection Bn? They are disjoint sets now, because Bn's are disjoint. So here I can apply the summation and runs from 1 to infinity mu of E intersection Bn. Now since Bn is a positive set, so that means mu of E intersection Bn is greater or equal to 0 for every member of sigma. So it's actually sum of non-negative number. The sum is also non-negative. It's greater or equal to 0. So which means that mu of E intersection A is greater or equal to 0. So that means this A, which is the union An and runs from 1 to infinity, is a positive set. Is a positive set. So countable union of a positive set is again a positive set. Is again a positive set. So next we have a very important theorem. I will write this as lemma. Because this lemma will give the assurance of the existence of positive set. Okay, this theorem is actually the existence of positive set. Positive sets exist. So if positive sets exist, the negative sets will also exist. So let's first prove this lemma. Then we conclude from this lemma that the positive set always exists. Statement. Let mu be a signed measure. Mu is signed measure है. It's a signed measure on this sigma, the collection of measurable sets, and let E belongs to sigma with phi set is always a positive set. You can see phi set, because mu of phi, क्योंकि इसका कोई भी सबसेट mu of phi क्या है, वो 0 है, ग्रेटर इक्वल टू 0 है, इसका मतलब ग्रेटर और इक्वल टू 0 है. उसका कोई भी सबसेट लीजिए वो भी phi होगा, उसका मेजर भी ग्रेटर इक्वल टू 0 होगा. तो phi set is always a positive set, but we want to find the non trivial positive set, जिसका मेजर पॉजिटिव होगा और वो पॉजिटिव पॉजिटिव सेट होगा. एक तो उसका मेजर पॉजिटिव होगा और वो पॉजिटिव सेट भी होगा. पॉजिटिव सेट का मतलब क्या होगा, उसके हर किसी सबसेट का मेजर भी पॉजिटिव होगा, ग्रेटर इक्वल टू 0 होगा, नॉन नेगेटिव. So let mu be a signed measure and let E belongs to sigma with mu of E is positive. So E is not here positive, okay? E is not here positive. इसका मेजर पॉजिटिव है मगर खुद ये पॉजिटिव सेट नहीं है. पॉजिटिव के लिए कंडीशन क्या है, इसका जो भी सबसेट होगा उसका मेजर नॉन नेगेटिव होना चाहिए. बट ये लेमा क्या कह रहा है, अगर आपके पास ऐसा कोई सेट होगा जिसका मेजर पॉजिटिव होगा, तो लेमा ये कह रहा है कि इसका एक सबसेट आप बना निकाल सकते हो इस सेट का जो पॉजिटिव होगा और उसका मेजर भी पॉजिटिव होगा. सो दिस थ्योरम गारंटीज दैट देन देयर एग्जिस्ट्स a positive set, then there exists a positive set, then positive set A such that this A is subset of E and measure of A is also positive. इसका एक सबसेट एग्जिस्ट होगा और इसका मेजर भी पॉजिटिव होगा और वो सेट पॉजिटिव होगा, ए खुद पॉजिटिव होगा. अब इसका मेजर, ये कंडीशन भी इंपॉर्टेंट यहाँ पर है क्योंकि एमपीटी सेट तो हमेशा एग्जिस्ट होगा ना, जो ई का सबसेट होगा. एमपीटी सेट हमेशा ई का सबसेट होगा और वो पॉजिटिव सेट ही है. एमपीटी सेट इज द पॉजिटिव सेट, मगर उसका मेजर पॉजिटिव नहीं है. तो यहाँ पर दो रिक्वायरमेंट्स चाहिए, एक तो ये सेट पॉजिटिव होना चाहिए और सेकंड कि इसका मेजर भी पॉजिटिव ही होना चाहिए. प्रूफ. तो इस प्रूफ में हम ज़ोनस लेमा का यूज कर रहे हैं कि बट आई विल नॉट एक्सप्लेन बिकॉज यू नो ज़ोनस लेमा, हाउ टू यूज ज़ोनस लेमा, दैट यू ऑलरेडी नो because you have done lot of courses where you have used this Zorn's lemma, like you have used the Zorn's lemma in function analysis where you have proved Horn-Banach's theorem. So you have used this Zorn's lemma in number of results previous semesters, so that's why I will not explain this how to apply this Zorn's lemma here. So let's start the proof. If for every measurable subset, अब E का मेजर क्या है? पॉजिटिव. अगर इसका हर कोई सबसेट जो होगा मेजरेबल सबसेट, उसका मेजर भी पॉजिटिव ही होगा, नॉन नेगेटिव होगा, तो ये तो खुद पॉजिटिव सेट होगा. इज इटसेल्फ satisfies the requirement of a positive set having major positive. If for every B belongs to sigma with B subset of E, with B subset of E, with B subset of E, we have mu of B is greater or equal to 0. Then E is a positive. Then E is itself a positive. Then E is a positive set. E is a positive set, and mu of E is greater or equal to 0. तो वहाँ पर A जो आपका है वो एक E खुद है, क्योंकि आपको E का कोई सबसेट चाहिए, वो E खुद काम कर रहा है. आपको E आपके पास एक ऐसा पॉजिटिव सेट मिल रहा है जिसका मेजर भी पॉजिटिव ही आ रहा है. अगर ये केस होगा, अगर इसका हर कोई सबसेट ऐसा होगा जिसका मेजर ग्रेटर और इक्वल टू 0 होगा, बट इट्स नॉट ट्रू इन जनरल बिकॉज दिस साइन एंड मेजर इज नॉट मोनोटोन. सो इट्स नॉट लाइक मोनोटोन और तो अगर इसमें अगर हर कोई मेजरेबल सबसेट E का ऐसा होगा जिसका मेजर ग्रेटर इक्वल टू 0 होगा, उस केस में क्या होगा? उस केस में E आपका पॉजिटिव सेट होगा. सो देन यू कैन दिस A is equal to E in that case. So let's assume that it has some subset. E has some subset having major negative, So assume that there exists some B belongs to sigma with B subset of E and its measure is negative, because if every subset has positive measure then we had done, so we have to take the second case. Suppose it has some subset, measurable subset with measure negative, Now by Zorn's lemma we can choose the maximal by Zorn's lemma. There exists there exists a maximal collection of negative sets. Maximal collection, fancy C, cursive C, you can say cursive C also, cursive C of cursive C of mutually, they are disjoint also, mutually disjoint measurable subsets of E, measurable disjoint subsets of E, such that mu of C is negative for every member C of cursive C. So C is maximal. So what's your C actually? C is this. C is those subsets of E such that C belongs to sigma and mu of C is negative, and this C is maximal in this, with this property. It's maximal with this property. This is maximal, okay, with this property. With this property it's maximal. This is your C. So C में जो भी सेट है वो क्या है, वो सिग्मा का मेंबर है और E का सबसेट है और इसका मेजर नेगेटिव है. तो ये जो कलेक्शन है, it's not empty collection because we have assumed that there exists at least one member having this property. We claim that this C is at most commutable. It's at most commutable. We first verify that. For this we first verify that this cursive C, it's a commutable union of cursive C's. It is C and n runs from 1 to infinity, where what is the Cn? Where this Cn, it's equal to C, the members of obviously members of C, they are members of C such that mu of C is negative, but here it depends on n, it's less than minus 1 by n. So each Cn is collection of sets actually itself. So how to verify this? It's verification here. It's verification. So let's first assume that suppose C belongs to cursive C. This means that C is a subset of is a member of sigma. C is also subset of E, okay, and mu of C is negative. So thus there exists n greater or equal to 1 such that mu of C is less than minus 1 by n. This is by Archimedes property, you can easily verify it. I'm not going to explain it here. How if the measure of sets is negative, if we have some negative number, then I can always find n such that that negative number is less than minus 1 by n. This is always this can be always done. So which implies that this C belongs to cursive Cn because it's a property of cursive Cn, okay, which implies that this C belongs to cursive Cn. So which implies that C belongs to union cursive Cn and runs from 1 to infinity. So that means this cursive C is subset of union of cursive Cn, because you have chosen this first, you have chosen this C from cursive C. And converse is real. Conversely, if C belongs to union and runs from 1 to infinity cursive Cn, that means this C belongs to Cn for some n, and this gives, if C is in cursive Cn, this means that this is by definition actually, this means that C belongs to C, okay, cursive C. This is the definition. C belongs to C. This is the definition of Cn. So thus this union because each Cn is actually subset of C, so we don't need to prove it actually here. This is subset of C, and hence Cn and runs from 1 to infinity. So actually we had to show that this C is at most countable. Now we will show that this Cn, each Cn is finite. Now we show that each Cn is finite. For if some Cn is not finite, then it contains a countably infinite set, then it contains countably infinite numbers, say C1, C2, because it's a collection of sets actually. So it contains these C1, C2, so on up to infinity. Countably infinite numbers of C, of cursive C, because each Cn is subset of C actually. So it's now countable. Okay. Now they are actually members of C. Also this mu of Cn, जो भी Cn आपको, it's negative. It's less than 0. It's some negative number. It is a negative number. It's a fixed negative number. So this implies that mu of C, let's denote this C by it's a union Cn and runs from 1 to infinity. So they are also disjoint because they are members of C actually. So we can apply the additive property here, sigma additive, and each number is negative number. It's a fixed some negative number, because you can see this because they are the members of C. So measure of each set is greater than 1 by n. So it's like greater than series n runs from 1 to infinity minus 1 by n, and that's equal to minus infinity, because series 1 by n is plus infinity. So it's minus infinity. Mu of C is minus infinity. So thus mu of C is minus infinity, where this C is where C is union Cn and runs from 1 to infinity. It's a member of sigma, and each Cn is subset of E, so C is also subset of E. Now let's find this mu of E. Mu of E is given to be positive, but mu of E is equal to mu of E minus C plus mu of C. Okay. But what is this mu of C? It's infinity minus infinity. So that means mu assumes the value minus infinity, so it cannot assume plus infinity. So this number is either minus infinity or it is a finite real number, and finite real number minus infinity is minus infinity, and minus infinity is again minus infinity. So it's equal to minus infinity, which is not the case, because which is a contradiction, because mu of E is positive, which is a contradiction. As it's given that mu of E, as it's given that this what is this mu of E, it's a positive, as it's given that it's in the statement mu of E is a positive, it is a positive measure. So that means each Cn is at most finite, thus C, which is union of Cn, is countable, is countable. So if it's countable, it means that the union of members of this C, it's C, where C belongs to, it's a countable. Each member of this C belongs to sigma, okay, and it's a countable unit because C is countable, so this also belongs to sigma. So here I am using the property that this cursive C is countable because you are taking the unit over countable set. Okay. Because this C is a countable class, it's like C1, C2, so on up to infinity. So each member is in sigma, so the union is also in sigma. It's in sigma. So we claim that the set A, which is equal to E minus D, which is in sigma, we claim that this set is a positive set, is a positive set. तो ये मेंबर तो सिग्मा का है क्योंकि ई भी सिग्मा में ही है और डी भी सिग्मा में, इनका जो डिफरेंस होगा वो भी सिग्मा का ही मेंबर होगा. अब आपको प्रूव करना है ये पॉजिटिव सेट है. पॉजिटिव सेट का मतलब क्या है, आपको प्रूव करना है इसका जो भी सबसेट होगा उसका मेजर नॉन नेगेटिव होगा, और आप ये भी प्रूव करोगे ये जो खुद सेट होगा इसका मेजर पॉजिटिव होगा, नॉट ग्रेटर इक्वल टू 0, इट इज स्ट्रिक्टली पॉजिटिव. The measure of the set is strictly positive. Okay, we'll show that this set is positive with its measure positive. So it's subset, it's because it's E minus T actually. So we have mu of E, which is equal to mu of A plus mu of D. Okay, and this is positive. Why it's this? Because our A is equal to E minus D and D is subset E. D is subset. D is here and this is E, this is your D. So this measure of E is equal to measure of D, this portion plus this shaded region. Okay, but what is the shaded region? This shaded region is E minus T, which is equal to A. So measure of this whole E is equal to measure of D plus measure of E minus D, which is equal to E. And this measure of E, its positive, is given. So that means both the sets must be these sets must be a positive set. I cannot say both the sets are positive. Okay, because D is not a positive set. D is the union of negative sets. So this mu of A must be positive. Mu of A must be positive. So this means that mu of A must be a positive set, because this one is not positive actually. This is the union of this is the union of it's union of actually negative sets. It's a union of sets having major negative. So this is a negative. This is negative number actually. This one. Okay, this is negative number. So this must be positive because the sum is positive. So first we have seen that this number is positive. Next we show that every subset of A has non-negative measure. Or if you take any member f of sigma, we show that mu of f intersection A is greater or equal to 0. So let's choose f. Let f belongs to sigma. Let f belongs to sigma. Let f belongs to sigma. Okay, let's try to prove this. Now we show that for any set say for any set B belongs to sigma with B subset of A, this should imply mu of B is greater or equal to 0. Means that every subset of A which is a member of sigma also has non-negative measure. Suppose it is not true. For if there exists some f, for if there exists some f in sigma such that f subset of a and f subset of a and measure of f is negative, suppose this is the case, then you take this this curses you union this f, this contradicts the maximality of C. This contradicts the maximality of C because this f is subset of as this f it's subset of A, so this C they also contain the subsets of A which are also disjoint from each other, so f is also disjoint from each member of C. You can choose this so this contradicts the maximality property of E, so thus this is not the case, thus A is a positive set. A is a positive set. And this E it's equal to A, it's equal to E union D union E minus D, it's equal to D union E minus D, that's it's actually equal to D union A, okay, it's equal to D union E, where this A is a positive set and this D is a negative set, this D is a negative set, where this A is greater than or equal to 0 and D is less or equal to 0, and they are also disjoint from each other. So thus we can say for any if E is a set of positive measure, then I can always find its subset of positive measure such that that subset is a positive set. So this proves this result. Whether this is negative or not, this is not done yet. So but this is a positive set. A is a positive set. So next we define Horn decomposition. Horn decomposition. What's this Horn decomposition? This Horn decomposition states that we can always find positive and negative set. There exists a positive set and negative set such that they are disjoint, and this X is equal to their union. Means that this full set can always be expressed as the disjoint union of positive and negative set. This is called the Horn decomposition, and this is always true for X because the set its measure is positive. So this theorem, we will do this theorem in the next lecture. Next lecture we will prove a theorem where we will show that Horn decomposition is always possible. Horn decomposition is always possible. And that we will do